So here they're saying, okay, I'm going to start here. Span of a set. I want us to discuss what is a span of a set. So let S equal to this be a subset of a vector space V. The set S is a spanning set of V when every vector in V can be written as a linear combination. So I have already explained how do you write as a vector as a linear combination. It's something like this. This is a linear combination. Or we can write the set S, which is this. It spans R3 because any vector can be written in this format. If you simplify this, it will still give you ABC. So now, this is another one. You can write it as a linear combination. So we can say that the above spanning set, it actually spans R3. Then we come. So every time they talk about a span, you must just perform the linear combination. I don't know what's wrong here. This is just chapter 1 only. So you must also know how to define a subspace. So here they say if V is a subspace, then W is a subset of V. Then these are the conditions. Additive, the zero identity must exist. Additive must exist. The multiplication must exist. Then let me scroll. You must also know the proofs, the intersection of a subspace, but I'll explain that later. So this is tutorial 3. They were saying express this as the linear combination of U, V, and W. So that's an interesting question. And also, which of the following are a linear combination of U? So I will explain this on the second recording. Then define linear independent. So you'll say let V be a vector space and S be a set of vectors B. Then S is linear dependent if and only if the equation will give you 0. And it means one of them is equal to 0. So this is just an example of the first one. Here they're saying they will multiply with A, B, C on every vector. And then they equate that with the 0 vector. Then you solve, you get your A, B, C. So you use Gauss, I think this is row echelon form. You convert it to row echelon form, you'll get, they got A, B, C. The A, B, C, I believe is that. It's equal to 0. Then you must also, so you must know how to check and also now the standard basis. A standard basis E1, E2 up to En. These are standard basis of Rn. So also have a standard basis of R3. They will be in this form. Then this is an example. You are given this, and then they say this will form a basis of R3. But how? They said they multiplied with X, Y, Z. Then they equated with 2ABC. After they used a row echelon form method. Oh, this is not a row echelon method. It's a Gauss elimination method. Then they solve, and they got 5. They got 5. The question was saying, does this form a basis of R3? So I'm not sure why they didn't actually conclude, but this definitely form a basis of R3. Then some important dimensions. If V is equal to 0, then the dimension of V is 0. For Rn, the basis, the dimension of Rn will just be n. For R3, dimension will be 3. For if this has n plus 1 elements, the dimension of the standard base Pn will be n plus 1. Then this one will be Mn. For this M matrix 2 by 3, the dimension will be 6. For continuous as a vector, it will be, the dimension will be infinite. So I think I will explain this, and then you must know how to define a coordinate of a vector. We say let V be a basis for a vector space V. Let V be a vector in V. We write V equal to that, and then C1 up to Vn is called the coordinate. So every time you write a coordinate vector, it must be in this format all the time. So this is a coordinate vector. The vector that has, so here they say determine the vector that has the coordinate with respect to the basis of this. So they took -3 times this, they took 2 times this, and then they sum, then they solve. This is their what? Their vector that has the coordinate vector of that. The second one, they did this, so this is the vector that will give us the coordinate vector VB. Okay, I'm going to stop here for now.